Hello and a very warm welcome to KognitoKey. I am absolutely thrilled to have you joining us today. We're diving into something that's totally crucial, yet usually hidden behind the scenes of our massive electrical grids. In today's explainer, we're going to figure out exactly how synchroscopes work and how they help us synchronize power generators safely. So think about it for a second. How do we actually safely link these massive power generators together? I mean, imagine the catastrophic risk if you tried connecting two roaring alternators to the grid when they're out of phase. We are talking about severe damage, massive electrical arcs, and literally devastating power outages. No way we want that. To prevent these kinds of grid disasters, engineers rely on a highly precise, ultimate hero device, the Synchroscope. Now, to get why this is so important, let's break down what we're actually trying to achieve here. To synchronize basically means we're taking machines of equal frequency and equal voltage and getting them to operate in parallel with each other, flawlessly. And the Synchroscope? Well, that's the ingenious device that shows us the exact split-second instant to make that connection. Because, when you're bringing a new generator online, timing isn't just a thing, it is absolutely everything. You can think of a Synchroscope as a sort of bridge of information. It uses a two-phase wound stator and a rotor. The stator, that gets its electrical supply from the existing alternator, the one that's already out there powering the grid. Meanwhile, the rotor gets its supply from the incoming alternator, the brand new one we want to hook up. By analyzing the phase shift between these two supplies, the Synchroscope instantly reveals any differences in phase and frequency. Pretty clever, right? And the best part is, this gives the operator incredibly simple visual feedback. If the frequencies of both machines match perfectly, the dial just sits there, completely stationary. But if the frequencies differ, the dial starts to rotate. And the speed of that rotation? It directly corresponds to the size of the frequency gap. So if it's spinning super fast, the difference is huge. If it's barely crawling, you know you are getting extremely close to that perfect synchronization. Okay, let's look at the first main type, the electrodynamometer type, which uses transformers and lamps. This particular design works in 3 really elegant steps. Step 1, the bus bar and the incoming machines excite the outer windings of a 3-limbed transformer, which induces magnetic flux. Step 2, these outer fluxes combine in the central limb to create a resultant electromotive force, or EMF. And step 3, a lamp connected to this central limb lights up. When the machines are perfectly in phase, that central EMF hits its absolute peak, and the lamp glows at its brightest. That moment of maximum brightness, that is your perfect instant to synchronize. But conversely, let's look at what happens when things are mismatched. If the voltages of the incoming machines are out of phase, that resultant flux actually drops to 0, meaning you get absolutely no glow, 0 light. And if the frequencies are completely different, well, the lamp will just flicker. Actually, it's pretty neat. The speed of that flicker perfectly matches the exact difference in frequencies between the two machines. Moving right along, let's look at our second category, the moving iron type, focusing on spindles and pressure coils. So this type features pressure coils that are linked straight to the incoming machine. By putting a resistance in one coil and an inductance in the other, it creates a perfect 90-degree phase difference between them. Because of this phase split, any mismatch in frequency will cause the spindle holding the iron cylinders to actually revolve. So simply by keeping an eye on the spindle, the operator can use the revolutions per second to accurately figure out the exact frequency mismatch. Now, before we wrap up, let's look at a fantastic real-world question from the comments. Vivek Singh asked, why does the Synchroscope pointer move clockwise and anti-clockwise? It's a great question. Basically, the direction of the pointer instantly tells the grid operators if the incoming alternator is running too fast or too slow. This means they don't have to sit there and guess. They instantly know, for sure, whether to throttle up or throttle down the incoming machine. And honestly, that is exactly how these incredible devices keep our entire power grid synchronized, stable, and safe. Thank you so much for watching this explainer on KognitoKey. If you found this valuable and want to keep expanding your technical knowledge with us, please make sure to subscribe to the channel, hit that like button, and share this explainer with anyone who loves learning how the world actually works. Before you go, ask yourself, as our grids shift more towards complex renewable energy sources, how will these traditional synchronization methods need to evolve? It's definitely something to think about. See you next time.